Welcome to Unit 5 nomenclature. For those of you at home, you do need to pause the video and copy that. All right. As mentioned yesterday, the title of our new unit is nomenclature, which is just naming compounds. Our most primary focus is going to be the three different sets of rules for naming three different types of compounds. Now remember, I introduced the word compound to you in Unit 1, which was anytime two different squares on the periodic table join together. All right, they bond is what it is. Our next unit after this one is called bonding, so we're going to get into the whys and a whole bunch of bonding stuff then. We just want to focus on naming them now. But in order to do that, I have to talk a little bit about, just a tiny bit about bonding, because I need you to know how to figure out the different types of compounds. One of the bits of essential info, though, is to make sure that your oxidation states are on your periodic table. So people at home, you need a periodic table and a polyatomic list, but make sure, as always, that your periodic table has those oxidation states. All right, so write them down where they are if your table doesn't have those. And always have those predicted charges on all future tables. Okay. The whole reason that items are going to decide to bond together is for the octet rule. If you remember, one of the things that we talked about during ionization is that most of the elements on the table are unhappy because they don't have 8 valence electrons, right? The only ones that do are the noble gases. So all of the other elements want to do stuff to become stable, and the solution is usually bonding to another item to fix their valence count. When they do that, they become more stable and they become happy. More on that next unit. What I need you to be able to do in order to name these compounds is to be able to first recognize, well, how do I know if it's an ionic compound or a covalent compound? Those are two different naming systems. So training you how to tell the difference is really important. So I want you to look at that second bullet there that says Ionics are, and then it gives you three things. We know that on your periodic table, there's this invisible staircase, right? And we know that that invisible staircase is dividing the metals and the non-metals, pretty much, right? That's what the whole point of it is. To the point where we know that everything over here is metal, except for hydrogen, and everything over here is non-metal. With that said, our first of three naming systems is going to focus on ionics, an ionic compound, which is new in terms of vocab. The way that you know that a compound is ionic and that it's going to follow the rules we cover today and tomorrow, this is the hardest set of rules. That's why it takes me 2 days to cover it. But look, it tells you on the slide how to recognize it. One of the ways is if a metal is bonding to a non-metal, simply meaning that the two items that are coming together, one of them comes from the left-hand side and one of them comes from the right-hand side of the staircase. Another way to say that same thing is a cation bonding with an anion, which is also what your screen says, because the line is also kind of separating those charges too, right? Because you know that all of these transition metals that use those Roman numerals, they're all positive, even though they can have different charges. So all of the metals, for the most part, are positive, and all of the non-metals, for the most part, are negative. So cation bonding with anion. A third way that you'll know that the rules we're about to cover today and tomorrow apply is if a polyatomic ion is bonding to anything. So you memorize these polyatomic ions, and I promised you that we would start using them now. So, but what the slide says is that if one of these dudes activates in a compound, it's a part of it, automatically ionic. So the first thing, really the most important thing to take away from the whole day is the 3 ways to know that, oh, this compound that he gave me is ionic and not one of the other 2. Then you got that big blurb that kind of summarizes everything we're going to do over the next 2 days. So, rather than dive right into the rules of naming, I want to demonstrate the chemistry on why we name the way we name. So, let's take a look at something. You don't have to copy that. I want to show you using Lewis structures the reason that compounds are going to form the way that we practice the next 2 days. So I want to show you how sodium and chlorine would form an ionic compound. Now, sodium lives over here, right? While chlorine lives over there, just in those general areas, all right? So with sodium and chlorine living in those general areas, do you see why it's ionic? Because a metal bonding with a nonmetal is an ionic compound. So if these 2 items are going to bond together, it'll be ionic. So here's what I'm going to do. In the margin of your notes, I want you to put sodium and chlorine kind of separate from each other. And I'm going to build a tally system as I draw some of these guys to do the octet. You'll see what I mean. For example, I'm going to start by drawing the Lewis structure of 1 sodium. So that's a little tally mark under sodium. How many dots does sodium have in his Lewis structure? Only 1, right? Because remember, the dots are valence electrons. Sodium is right there, and all of the elements in group 1 have 1 valence. Do you agree? Okay, so 1 valence electron. I also want to draw a chlorine because we're going to form a compound and make them bond together. So let's draw a chlorine. How many valence electrons does a chlorine have? 7, right? Because we know that chlorine is hanging out way over here in group 17. Therefore, he's got 7 valence electrons. So draw them. Remember when we did ionization, there's actually 2 valence counts that make an element happy. One of them is 8, the octet. What's the other good number? 0, right? If they can empty out, that also makes them just as happy. So look at sodium and chlorine. If I was going to move the dots around, do you see a very logical way to make them both happy? What could I do? I could move sodium's valence electron over to that spot on the chlorine. And if I did that, it would make sodium be naked, essentially, which makes him really happy. Sodium loves being naked. And it would fill chlorine up. And all I had to do in order to make this work, I started us off with a really easy one, but all I had to do to make everybody happy was, well, draw 1 of each. Move that dot over there, 1 of each, which means if sodium and chlorine were to bond together, they do so in a 1-to-1 ratio, all right? That's the formula for sodium chloride, because I only need 1 of each of them to make the octet happy everywhere. And that might seem really simple to you, but when I show you our next example, you'll see that it can get a bit muddier. So if you're going to bond these together into an ionic compound, metal with a nonmetal, you only need 1 of each, which is why there's no little numbers, no subscripts. Let's do a more fun one, though. Again, in the margin of your notes, and this margin thing will make more sense this time. I want to bond aluminum with oxygen. So let's keep our tally system so that we can keep track of what we draw. Let's go talk to somebody. Let's go over to cluster 5 and talk to seat 5. Hey, Aspen, if aluminum and oxygen are going to form a compound, would it be ionic? She says yes. Do y'all agree or disagree? It's very simple. It's very simple. Hey, is aluminum on one side of the zigzag? Yeah. Is oxygen on the other side of the zigzag? Then it is ionic, metal to a non-metal. Very simple to figure out that it would be ionic. Stack. All right, so it would be ionic. All right, so let's figure it out. So here we're going to go. We're going to do the same thing. Do it with me. I want to start by drawing an aluminum. All right, this is just my tally. I'm going to draw one aluminum. So let's draw an aluminum. All right, now look at aluminum's location. All right, where, or rather, how many valence electrons does aluminum have? 3, because group 13 has 3. All right, let's also draw an oxygen. Starting with one oxygen. Find oxygen. How many valence electrons does oxygen have? 6, because everything in group 16 has 6. So draw them. All right. Now remember, last time they just clicked right together, and one of them went empty while the other one went full of 8. Let's see if that happens again. Now we know aluminum wants to lose electrons and oxygen wants to gain electrons. We've already been tested on that. So let's start moving that around. Let's put this valence electron here and this valence electron there. If we move it like that, is anybody happy? Yes, who's happy? Oxygen is. If you fill him up on those 2 dots, oxygen has 8. He is happy. But what is wrong? We've actually made aluminum angrier. Do you remember the closer they are to the octet, the more crazy reactive they are? Aluminum is now only 1 dot away, and he's going to throw a fit. So we can't stop there. Now, considering we can only use aluminums and oxygens in this example, what could we introduce to the whiteboard as a outlet for this extra electron? We can only use aluminums and oxygens in this example. What could we throw out there? A second oxygen. Let's introduce a second oxygen. There's a brand new oxygen. How many valence electrons does oxygen start with? Always 6. Oxygen is in group 16. He always starts with 6. And check it out. I now have a way to make aluminum happy. Watch, watch, watch. I could just move this electron there. Is aluminum happy now? He's very happy. All 3 of those dots have been moved away. He's naked, 0, stable. Is everybody happy? Who's mad now? Oh, oxygen mad. No good. Let's fix it. So, what can we introduce? Remember, we can only mess with these 2 dudes. All right, so let's introduce a second aluminum. How many valence electrons does a new aluminum always start with? Group 13, always 3. Just go look it up. All right. Now remember, we did that because oxygen was unhappy. Let's fix oxygen. Let's track our work. This aluminum has all of his dots gone. He's happy. This oxygen surrounded by 8 from the movement. He's happy. This oxygen surrounded by 8 from the movement. He's happy. This aluminum, no matter what we do, we keep making people mad. So we've got to keep going. What can we introduce to make the aluminum happy? A third oxygen. Let's add another oxygen to the whiteboard. Oxygen from group 16 has 6 valence electrons. Anybody see a happy ending in sight? As we make the angry aluminum happy, you'll see that everybody is suddenly happy. All of the aluminums are empty, all of the oxygens are full. What's the point? What's the point of all this? Well, here it is. If aluminum and oxygen are going to form an ionic compound, ionic because one of them is metal and the other one's non-metal, the only way they can do it is if you have 2 aluminums and 3 oxygens. This is the only way that they bond together is by Al2O3. Why? Because of the dots, right? That's why. There's no other way for them to bond together without falling apart. So sodium and chlorine, 1 to 1, and we proved why. Aluminum and oxygen, 2 to 3, and we've proved why. The octet rule. Now, here's the good news. If you don't like everything I just did, you don't have to do this. What I need you to be able to do is if I give you a random metal and non-metal and I say they're going to form an ionic compound, I need you to know those 2 numbers very quickly. It would be annoying if you always had to draw the dots to figure it out. So I have a shortcut that I'm going to be obsessed with over for the tomorrow and the rest of today on how to come up with these numbers without drawing the dots. But I don't want you to forget about the dots because what I'm about to show you is just a secret set of rules that isn't really chemistry. It's just a way to do this quickly. But y'all, this is what's always happening. All right, every time we've come up with one of these, it's because of this. I just don't want you to have to draw that. Here's the shortcut. We're going to practice a bunch of them, but let me ask you this. Looking there and considering that aluminum is right here, all right, here, what is aluminum's oxidation state? Aluminum's oxidation state is +3. Oxygen is over here. What is oxygen's oxidation state? -2. The skill we're going to practice is the fact that if you take those 2 numbers and you crisscross them, they become the proper formula. And it works every single time. Al2O3. Any questions before I change gears to straight practicing? All right. Whoa. Got you dizzy. All right, y'all. Let's practice some ionic nomenclature then. Write that down. Is that going to be ionic, lithium and nitrogen? Yes, because lithium is to the left of the zigzag, nitrogen's to the right, right? It's easy. It's the most important part, though, because when I introduce the other compounds, you can get mixed up at that step. All right, it's ionic. Here we go, here we go. What is the formula for lithium? Li, the symbol I meant to say. Somebody else, what is the symbol for nitride? Yeah, it's just N. Remember, your opening slide says this, but if you see that "ide" at the end of a word, it's really just an element on the periodic table, but bonded. So nitride is really nitrogen. The oxidation state of lithium is +1. Verify that you can find the +1. Stop me, call me over if you can't. The oxidation state of nitrogen is -3. Call me over to your desk so I can point to why if you don't know why. Do you see how I didn't write the plus and the minus? It's important, it's there, but the charges themselves don't actually play a role in our shortcut. So sometimes they actually just confuse you if they're there. Whatever, I don't care if you write them or not. I need the numbers to do this skill. So here we go. You ready for the crisscross? The 3 becomes lithium subscript. The 1 becomes nitrogen subscript. And the final formula for lithium nitride is what? Li3N. Don't put the 1. We never show 1s as subscripts. Water would be annoying if it was H2O1. So we could draw dots, all right? You draw 3 lithiums and 1 nitrogen, and it would make all the octet happy. But instead, we use the crisscross cheat. The only way to write lithium nitride is Li3N. Let's draw some cards. Make sure you're writing these examples as they appear. You need full notes. All right, let's go get some help for potassium oxide. Let's go over to cluster 3, seat 4. Hey, 3, 4. What is the symbol for potassium, Amber? Just the symbol for potassium. Yeah, here. So look forward to the left. It's in the first column. K. Yeah, potassium is K. All right. Oxygen, or rather oxide, is really just oxygen, so it's O. Let's go over to cluster 6, seat 4, Aspen. What is the oxidation state of potassium? All right, +1. All right. Let's go over to cluster 3, seat 1. Hey, 3, 1. What is the oxidation state of oxygen? -2. Everybody all right? What are we going to do with them numbers? Crisscross. The only way to write potassium oxide is K2O. It's ionic because it's a metal bonding to a non-metal. Does this seem easy so far? You think I can make it more annoying? I bet you I can. I don't want to, but I bet you I can. Do that one by yourself. Why? Because it's in a different color font. Radium sulfide. go pick on somebody. Let's go over to cluster 1 and talk to seat 4. Hey, 1-4, just read me a formula. Wait, what'd you get? What's the answer? Do y'all agree or disagree? Somebody that's saying disagree, what did you write? Ra2S2. How did you know to do what you did? Watch, because I set you up for failure. All right? The reason that a lot of y'all got Ra2S2 was because you saw that he's +2 and he's -2. So you crossed them. Well, here's the first of many annoying side rules. Write that down. I guess I can show you people at home what it says. Our first side rule states that if the charges can reduce based on each other, then they do so before the cross. What does that mean? Well, you see these two 2's? If you were to put them as a ratio, it would be, well, 2/2. And what is 2/2 reduced down to? 1/1. So these are the numbers that would need to be crossed. And if you cross a 1 each direction, you'll get actually the first answer that was put in, RAS. All right, and if you're thinking, well, why? Why does that rule exist? Because it's the dots. It only takes 1 radium and 1 sulfur to make the dots happy, the way it did at the very first example that I showed you. So if it was 3 to 3, it would be the same. That's true. All right, let's take a look at this one together. Plumbic selenide. Ooh, what's plumbic? We're doing this one together. All right, same thing, but plumbic looks a little weird. Hey, look at the side of your polyatomic list that you didn't have to memorize. I want you to look at the quiz 3 section and see if you can find the word plumbic anywhere on your polyatomic list. What do you see? It's Pb. Not only is plumbic Pb, what charge does plumbic have? +4. Make sure everyone can see. Look in the quiz 3 section of your polyatomic sheet and prove to yourself that plumbic is Pb +4, yeah? All right? Do you see it? What about selenide? What element is selenide? It's just selenium. All right? What is selenium's oxidation state? -2. Selenium lives in group 16, so it's -2. Y'all, look at those oxidation states. What do we need to do before we cross? Reduce them, right? It's a 4-to-2 ratio, which reduces to a what? A 2-to-1 ratio. So don't cross the 4 and the 2. You cross a 2 and a 1. Plumbic selenide is PbSe2. It's the only correct way to write it. Questions? We already reduced it. We crossed the 2. It's now a 2-to-1 ratio, so it can't be reduced anymore. All right, we get out of here in 4 minutes, right? Yeah. I'm sorry? No. Not this close. Yeah, I don't want to cut off here, but stupid day is going to make me cut off here, I guess. All right, so we've got tomorrow to continue this lecture. Don't do anything on Canvas yet. You are not prepared until you watch the other video or experience the other lecture.